Everyone, there's two sheets. Gosh, I think this is called Progress Quiz 6.3. Was the one that I gave you for homework 6.3, or was that 2 at least? Phew, good. Okay, at least I didn't give you 6.2 3 times in a row. So there's two problems here. They are the same kind of starting questions. Some of you just double check. It should say 50 Newton push right here. Some of the paper copies I printed say 0 newtons, but there should be a 50 there. If you're watching this because it's a snow day today, what you are going to have to do is you're going to work through these two problems, hit pause, right, in like a couple seconds, then turn it back on. We'll work through these two problems together. Then you, as a snow day, B-Day group, will turn this in as a practice to learn assignment for your Thursday snow day, but it's not really a snow day because it still counts as a day of school day thing. If you are an A-Day student and it is a snow day, you're just going to do the assignment that was assigned to you that we'll talk about a little bit later today. So it's a work on a worksheet day. That's not this. So just so you're aware. So I'm going to ask you to work on this. I'm going to give you a little bit of time. Then we're going to go through and walk through these two problems kind of together. This one, no friction. This one, there is friction. This one, I'm asking for the velocity at the bottom. However, in this problem, part B, I'm giving you the velocity at the bottom. I'm giving you the V2. And the question is a little bit different question than we've asked you before. It's asking what is the force of friction. And the way you're going to determine that force of friction is from the work done by friction equation. Okay, so just kind of keep that in mind. So people in person, you're going to work on that, and we'll go through it kind of together. People watching the video, hit pause, and when you have them done as far as you think you can do, then unpause, and we'll work through these on the video. So I drew a picture. You, 60 kilograms, are at George Street Hill sledding with your bestie. You are sitting on your sled trying to, do we say besties anymore? Probably not. Yeah, no, this is a while ago I wrote this one. I was cool and hip back then. Sure. You are sitting on your sled trying to go down the 15-meter tall hill, but you are only moving 2 meters per second. Your friend decides to help you out and gives you a 50 Newton push for 2 meters before they fall down. How fast will you be moving at the bottom of the hill if there is no friction? So you, 60 kilograms, applied force of 50 newtons. They only push you for 2 meters. The hill is 15 meters high. It's going to be a 2-location problem, so we're going to want to know H1s, H2s, B1s, D2s. So in this particular problem, it says the hill is 15 meters high, which makes it easy if we say H1 is 15 and H2 is 0. And then we're kind of set, there's no springs. Eventually what's going to happen is we will be using the work in plus the work done by friction is equal to our change in mechanical energy, which remember that expands out to, well, it expands out. I'll do that in a second. But we should address those two things first. So work in, the equation from your blue formula sheet for work in is plus or minus our applied force times our displacement, the displacement of the push of the applied force. This is specific to how far is this force applied over. So our work in is going to be plus, because my applied force and displacement are in the same direction, of 50 times 2. Your bestie puts in 100 positive joules worth of energy into the system. I'll write it, but the work done by friction is going to be minus the force of friction times our displacement. However, it says that there was no friction, therefore friction does 0 work on this problem. Now I'll come back over to here. So work in plus work done by friction, we've talked about, and I did those two already. So if we expand this out, ME2 minus ME1, ME2 is those 3 energies KE2, PEG2, PEE2 all added together. Final minus initials minus KE1, PEG1, PEE1. Okay, so that's what where we're at. So, if we go through and say, is there work in? Yeah, there's work in, 100 joules. Work done by friction, frictionless in. Are you moving at the bottom of the hill? The answer is yes. Is there a height? We find the bottom of the hill to be 0, so no height at the bottom, no spring at the bottom. At the top of the hill, we were moving at 2 meters per second. Your friend didn't think you were going fast enough, so he gave you a push. Yes, you had a height, but there was no spring. Work in is equal to 1/2 mv2 squared. That's your KE2 piece. Minus my KE1 is that 1/2 mv1 squared, but then we have to add it to m times g times h1. Notice how I have these two things in parentheses because they're in parentheses there. We start plugging in numbers. Work in is going to be 100, 1/2 times your mass times v2 squared. That's what we're solving for. Yes, gosh, I used a lot of parentheses already, so technically, color code. This is the parentheses around everything on the outside. Minus parenthesis 1/2 60 v1 is 2 squared plus 60 times 9.8 times 15, and that closes that outer set of parentheses. One half of 60 is 30 times v2 squared is 30 v2 squared minus, assuming I did this algebra right, let me know if I messed something up, but 1/2 of 60 times 4, 2 squared, I'm sorry, is 120. Then 60 times 9.8 times 15 is 8,820. We combine, we add what's in the parentheses. Then I can't combine this is v2 squared, there's no v2 squared, so we got to add, and then what we have over here is 9,040 is equal to 30 v2 squared. Divide both sides by 30. v2 squared is equal to 301.33, which then when you take the square root, v2 is 17.36 per second. Assuming I did my algebra right. Before I erase that, I'm going to start I'm going to draw my new picture just because if you're still copying that, but I'm going to erase that in a second. So the new problem is similar. You're on top of George Street Hill. You're going 2 meters per second. Your friend pushes you 50 meters with a 50 Newton push for 2 meters on top of a 15 meter high hill. But now this time, Frank is driving past and uses his radar gun to clock you at 10 meters per second. It references a Fight Club, because when I wrote this, there was like boys fighting in the bathroom that they called it Fight Club, and they were just beating each other up, but the rules were no punches in the face, because then you could see, it was weird. It was kind of this, it was a thing. I don't know why, but it was a thing. No, actually, I think when I actually wrote that, that was a couple years later. I think this was where there was like some video of a kid fighting another kid from like in the bathroom during a basketball game. I think that's what it was, and that was called like, all right, whatever. Don't do it, it's silly, don't do it. That's what the Fight Club reference is, whatever. The thing that's different about this one is now there is friction. And the reason you aren't going 17 meters per second is because friction is going to slow you down. Now the ultimate question is, what is that force of friction? And the way we're going to get to that force of friction is in that work done by friction equation. Now, the one thing I do want to point out, when we talk about the work done by friction, it's the force of friction times delta x. This delta x is the distance that friction acts over. And it says that the hill is 50 meters long. So it's saying from here to here is 50 meters. So when we use that, that's going to be that number right there. But our setup is very similar. We're starting with a 2-location problem. Two-location problem. Work in is something that we need to calculate. However, it's still work in is plus or minus our applied force times displacement. Our work in is going to be plus 50 times 2. It's only 2, it's not 50, because the push is only over 2 meters. It's the exact same work in as the previous problem, so our work in is going to be 100. So as we kind of work through that, yeah, there's work in, yeah, there's work done by friction. We just don't know, this is what we're solving for. That's what we're going to solve for. Yes, moving at the bottom, no height at the bottom, no spring at the bottom. Yes, moving at the top, yes, has a height at the top, no spring at the top. Very similar setup. Okay, that's what those equations look like expanded out. Again, solving for that. Now I'm plugging in numbers. Oops, that's a minus, sorry, minus, screwed that up, minus, that needs to be a minus right there. Minus 1/2 62 squared 69.8. Now I'm going to go with that I did these calculations right and I didn't screw up the algebra. However, if that's not the case, let me know. I screwed something else up again. V2, I know V2 this time because Frank was driving by this is 10 squared. Sorry about that. So 1/2 60 times 10 is 3,000 minus parentheses 120 plus 8940. Got to do the addition first. After you do the addition in parentheses, then 3,000 minus this is going to give you a negative number. It's going to be negative 5,940. I want to get that by itself, so I'm going to have to subtract 100 from both sides. The work done by friction is equal to negative 6,040 joules. Last step of that problem, it's asking for the force of friction. So we're going to plug that number into our work done by friction equation. Negative 6,040 is equal to negative force of friction, which is what we're trying to determine, times the length of the hill, because that's how far friction acts over. And that's a negative and a negative, we end up with a positive of 120.8 newtons. Is what I came up with. Now, a couple of you had a couple numbers different, and I'm not sure why, but so that's these two problems. And again, this is getting near the end of like material that we're going to cover. So if you are watching this video as a snow day, B-day, virtual day, make sure you get this, submit a picture of these two problems into Canvas. And that'll be your snow day assignment. So that's that. Then for tomorrow's homework, your virtual day homework is going to be a worksheet called Lack of Conservation 1. Lack of Conservation 1 is the homework assignment for you on your virtual day. Yes, B-Day students, this is also your thing. I don't know if I'm even, it's called Lack of Conservation 1. So this is something you're going to work on. The thing I do want to point out really quick for problem 1 on here, treat this as an ME1 problem, treat this as an ME2 problem, and then it's really just what's the difference ME2 minus ME1. That's what we're looking at there. So other than that, most of these problems kind of follow that guideline. So that's your virtual day for assignment, and have a good weekend, everyone.